Hello everyone, today we are going to discuss the longest increasing path in a matrix question. In here the requirement is that we have to find the longest increasing path that we can find in this matrix. So if you can see, if we start from 1 and take this particular path, this will give us the maximum number of values that we can cover at the end of the day, that is 4. And let's take this example. Here you can see, you might think, okay, I'll start off with 1. No, if you start off with 1, you can either go till 1 and 2, 1 to 2 or 1 to 6. That's it, you can't go more than that. But if you start with 3, you will see that you will be able to cover more values, that is 3, 4, 5, 6, and in turn the answer will be 4. So at the end of the day, our task is just to find the longest path. We do not care if it is starting from 1 or it is starting from what value it is. We do not care about this. Second thing to analyze over here is, it doesn't need to be sequential. Like, it doesn't need to just be 3 plus 1 4 plus 1 5 plus 1 6. No, it can be in random order as well. It should just be increasing. That's all the requirement is. So if you see 1 2 6 9, there is no particular sequence that we can see, but still it is increasing, and that's all we care about. Okay, the third thing to keep in mind while solving this question is, it should be strictly increasing. It can't be, okay, 1 and 1, both of them are equal, so we will not consider equal value as the increasing path or the increasing sequence that we are looking for. So if you take care of these particular 2-3 things, we should be able to come up with a good solution over here. So definitely when you went through the question, it's very clear that we have to apply some sort of DFS to take one point, go until the very end and tell me what is the length we are getting from here, and then explore the other path and get the maximum length from there, and then explore the other part, get the maximum one out of there, and calculate the whatever maximum we are getting every time, get me the maximum at the end of the day, and that's what I will return. Correct? This was the first intuition that came to our mind, and that's all we have to do. We do not have to apply anything fancy. We just have to go do a simple DFS approach, where we will be taking one node and exploring all 4 directions, and if we are able to find the increasing subsequence, or if the current value is more than the parent value, then we will consider this value and we'll continue with the DFS approach for the same node, that okay, now explore the other 4 nodes as well, up, down, left, right. That's all. Okay, so I think we are good to go with the question then. Let me think if okay, one more thing that we should be ready with. You could do this purely with recursion. You do not have to do any DFS calls. Any DP metrics you do not have to make. Pure DFS will work. Start with 1, explore all directions, explore all the directions, so and so and so on. That will work, but that will give you a TLE at the end of the day. Applying pure DFS without memorization will give you a TLE, and that's the case with most of the scenarios. If you are doing any grid problem, make sure that you are using DP at the end of the day, because for small test cases your code might run, but for big test cases you will require a memorization solution. Fine. Now you might ask why a memorization solution is required on top of DFS for this particular question. So see, you started off with 1. Okay, you are exploring all 4 paths, right? I'm just giving you an example that this is the starting point which you are starting for. You are exploring all 4 paths. From this path you end up at position 6, let's suppose, and from this position you took some different path, that is this, and you end up having you are end up visiting the same node again. So you can see that there is a overlapping sub problem. We can visit this point again and again and again. There should be a way to save the current value, to save the possible path that I can cover from here, which will give me the increasing path in the matrix. And once I have that path, I just need to add 1 to it to make sure that what will be the maximum path which I can reach from 2. What I mean by this, let's suppose I'm asking what is the maximum path that you can reach from this node. It will say it is just 1 2, that is 2 6 and 9. So it is just 2 box that we can cover. Fine. So the answer here is 2. Now I'm asking that what is the maximum number of box I can cover from here. So you will say whatever is the maximum one over here, add 1 to it. So 2 plus 1, 3. That means if I start from here, I just need 3 nodes. And the same thing I'm asking, that what is the maximum value we can get it from here, to get what the children can reach out to, and add 1 to it, so that children on the max can reach out to 3 nodes. So I'm just saying 3 plus 1, 4. That means I can reach out to 4 maximum nodes at the end of the day. So that's how DP is working. You are saving the particular box with the value that represent the increasing path, the longest increasing path from this node, and then you're going back to parent and adding 1 to it. That's all you are doing. So let's quickly go through the code. I have declared a DP, a directional array which represent all the 4 direction, up, down, left, right. I have a length with me. I have declared a DP array as well. So this DP basically represent currently it is 0, but at the end of the day what we are expecting, it will give me the longest path from this particular node, or from this particular node what is the maximum path that I can reach, from this particular node what is the maximum path I can reach at the end of the day. Fine. Okay, that's all we want. Right now let's see what we will do. We will go ahead and explore each of the node one at a time, explore each one of them. Okay, and we will ask that what maximum can I get if I start with this node. So we'll get an answer through DFS. I'll say, what if I start from here, what the max you can give me. I start from here, what is the max you can give me, and so and so and so on. Okay, and at the end of the day I'm taking the maximum one out of it and saving it, or returning that value. So that's one part. Now the other picture is how we will write the DFS call, because for every point we are expecting that this point will give me the maximum the longest increasing path that this particular value can have, or this particular index row comma column combination can have. That's all we want, right? So for that we are using a DFS call. Okay, we will explore all 4 directions, and we will keep on calculating the maximum value that we will get from all 4 directions, and get the maximum one out of it. That's all we will do. Okay, so before moving ahead, we will have a base case where we are saying that we should not go out of bound. When I'm exploring all the 4 directions, I should make sure that I'm not going out of bound. Second thing I'm making sure is that the current value that I am on right now, let's suppose I'm starting from here, I'm exploring all 4 paths. So this got neglected because it is going out of bound. This got neglected because I went out of bound. This will get neglected. Why? I'm asking why this will get neglected. This will get neglected because this value is not more than the parent value. That's the condition that we are putting over here, that this value should not, if it is not more than the parent, then we will return 0. Fine. Let's suppose from 9 you went to 6. You can't go in this direction. Why? Because you will check, is this value, is this value, what I'm checking is the value that I have with me. If it is less than or equal to my parent value, then there is no sense, because I want the increasing subsequence and not the decreasing subsequence. Okay, so if this is the case, then I'll not go forward, I'll just return 0 out of it. So for all these conditions, there is a base case that it should not be out of bound, and the parent value should be smaller than my current value. If that's the situation, if that situation is not covered, then return 0. Fine. The second point we are doing, which we are checking if this particular box or this combination of row and column is already visited. If it is visited, do not calculate it again, because that will give you TAT at the end of the day, because there are a lot of ways to reach 6, right? You can start from here, then reach 6. You can start from here, then reach 6. You can even start from here and then reach 6. So there are a lot of ways through which you can reach 6, right? So there is no sense in calculating this particular combination of row and column again and again. So for that reason, I'll just say if it is not equals to 0, that means it is already visited, and give me the value that is saved over here. Once that is done, what I'm doing, I'm exploring all 4 paths. Okay, and when I'm saying I'm exploring all 4 paths, what I'm doing, I'm calling this helper function with this with all 4 directional values, and I'm getting the value out of all 4 of them, all 4 direction, and I'm getting the one which will give me the maximum value. And once I get the maximum value, I'll add 1 to it, saying that okay, this value will now be included as well. So that's why I'm adding 1, and I'll save that value in my DB row comma column, because in future if I have to do it again, or if in future I end up in that particular position again, I do not have to calculate it. I can just use the memorized value that I just used. So that's all. It's a very easy DB problem. The only trick here is to figure out that okay, it should not go out of bound, and it should also make sure that the current value that we are looking for should be bigger than the previous value or the parent value. So that's all. It's very easy DFS problem. If I have to discuss about the time complexity, so if you see, when it comes to time complexity, right, what you're doing, you are exploring each node at the end of the day. Here you can see that you are exploring each node at the end of the day, and here also you will be reaching each node just once, because every time when a call reaches to a particular node, we are saving it as well, right? So we do not have to revisit a particular combination flow and column again and again. We can just take that value, save it, so in the future we do not have to go over all the calls again and again. We can just drop out from here. So the time complexity is just row into column. So this means that these are the only particular combinations that we will be visiting at the end of the day. If I have to talk about the space complexity, it will be again R and R into C, which represent that we will be using a DP array, which will be of this particular exact replica in terms of dimension with the matrix. So that's all, I guess. So using a DP was really helpful, otherwise we would have visited the same node again and again. And this is the space and time complexity. I hope this question helped you, and I'll share this particular piece of code in the comments as well. Hope this helps. Thank you.